So for today, we're continuing our series on infection risks in the environment of care. Today, we're going to talk about facilities, air handling, all those things that intimidate infection preventionists. We have Larry Lee here. He's a certified industrial hygienist. He's also a very active member of our Puget Sound chapter of APIC and does a lot of work for infection preventionists in hospitals around Washington State. So with that, I'm going to let Larry introduce himself, and we'll take it from there.
All right. Thank you, Jamie. Hi, everyone. This is Larry Lee here, coming to you by the internet. It's sort of a new thing for me. I'm a little unfamiliar with it, but I figure I'll get better by the end. I am a certified industrial hygienist, and industrial hygiene is a profession very much very similar to infection prevention, and we view the world through sort of our own paradigm, which is the anticipation, recognition, evaluation, and control of hazards. And so in 1996, I was a newly minted and certified industrial hygienist, and I got a call that ended up changing my life. It was from a downtown Seattle hospital, and they had an issue with a sewage flood. Apparently, a 48-inch sewer main had broken, had backed up and flowed into this hospital at ground level, flooded nuclear medicine and radiology, found penetrations in the floor that then started to, quote, rain down in central sterilization and supply in the instrument sorting area. It pooled on the floor there and went down half a floor into the HVAC system that served the entire hospital. So it was sort of a inauspicious, crappy way to begin the rest of my career, but you know, who else was going to do it, I thought. So sewage cleanup is pretty standard stuff for us. You know, yes, it's unpleasant. Yes, it's, well, we'll stick with unpleasant, and not necessarily fun, but we know what the hazards are. But it took us a while to dry the place out, and some fuzz started to appear on the walls, and I was asked, is this a problem? And I didn't know at the time, so I went and checked it out, and I learned that, my gosh, it is a big, huge problem in healthcare, having mold growth inside. And so from that moment on, I basically decided to specialize in healthcare construction and infection prevention, and it rejuvenated my career and brings me here to you today. Now, what I'm going to speak about today is the facilities, is really the mechanical systems of the building within the environment of care. And I try to see this as simply as possible because there's a ton of jargon and a ton of terminology that goes along with these systems, but I try to break it down and keep it simple. So basically, if we have a building, we have the outer structure, which is referred to as the building envelope, and everything that happens inside that is where the environment of care is. It's where we provide care to our patients, and that mission is supported by the mechanical systems. The first being the heating, ventilation, and air conditioning system that I'll refer to as the HVAC or HVAC system, and also the plumbing systems. And again, keep in mind that I'm going to do my best to keep this simple because it really is pretty straightforward, and there's really no better way to do things simply and straightforwardly than to use stick figures for this. Now, for infection prevention purposes, the building interior, in terms of HVAC, it really helps separate the outside from the inside. We want to keep the dust and allergens that are outside. We want to keep non-sterile particles, such as soot from air pollution, outside, and mold spores, of course, because they present a risk to our immune-compromised patients. And the HVAC system does this through the use of pressure and pressurization, air filtration, and air exchange. So keeping it simple, if you'll look at this diagram, this beautifully hand-drawn diagram, we have the outer building envelope as represented by the outside edge of everything here representing the building. And we have the outside represented by the sun and the birds flying by. And so to start, the air handling unit, which is really the lifeblood, the pump of the HVAC system, they typically are found on roofs, not always, but generally on roofs, and fresh outdoor air is drawn in through a set of louvers by a fan that's inside the air handling unit. It is pressurized and pumped into ducts and pumped and delivered to rooms. So because we're pumping in air, the room becomes positively pressurized, meaning that any point where there are leaks, such as windows or doors, that extra pressure inside the room is going to be forced outward. This is how we pressurize the building and how we keep the outside stuff outdoors and the inside stuff indoors. Same thing for this other room, which represents my operating room. The air is pumped in, and wherever there's leaks or openings in doorways, that air pressure moves out, and so it keeps airborne things out. Okay, I'm still working on my technical difficulties here. Here we go. So the second half of this is the exhaust. We pump air in, air also is required to leave. So if we stick on the operating room side, we have the supply air coming in, and that grill down at the bottom, there's usually one in every corner or every side of your operating room, is where the exhaust air is sent out. There's a grill, there's a duct that's inside the wall that leads its way up to an exhaust fan that does nothing but pump air outside the building and exhaust it straight out. That's typically what we'll see in an operating room would be a designated exhaust. But over here on the left side, in a more standard room, we would have the air coming in, but we will recirculate some of that air through a return air grill, which is also ducted back up to the to the unit, to the air handling unit up on the roof. So we're able to maintain positive pressure because we have more air being delivered than we have air being sucked out. So this recirculating sort of cycle of air in an office is rather typical. A portion of this air is mixed with the fresh outdoor air that's coming in, and a smaller portion is exhausted up the top out. But the net effect is that there's always more air being pushed in than is being sucked out in a normal office as well as an operating room. So this is real simple stuff. Now, these relationships are defined by the 2010 as well as 2014 FGI guidelines. So they tell us what these relationships need to be inside the building. So for our operating room suites, for our clean utilities, for our sterile supply areas, for our pharmacies, these are spaces that are required to be positively pressurized to keep stuff out of them. So the net flow of air is into those rooms, and the excess air that's in them is pushed out through doors and windows and openings and things like that. There are also negatively pressurized spaces that have to keep stuff in them, like airborne infection isolation rooms to isolate the patients, laboratories to isolate odors, dirty utility, bathrooms. They're all required to be kept negatively pressurized, and that's all found in the FGI guidelines. Now, you're going to see throughout this talk that I refer to the 2010 FGI guidelines, and that's because I lent a colleague and friend of mine borrow my 2014 guidelines, and he didn't give them back to me until last night. But I can assure you that the information is still the same from guideline to guideline. So there's pressurization. The next piece is filtration, filtering the air. The filters do two things. They were originally designed to protect the fans from grit and extend the fan life. The other piece is, as we've moved on, is to protect staff and patients and visitors from that stuff that's outside. We want to filter a portion of that out. And this, again, is also found and detailed in the 2014 and 2010 FGI guidelines. So this chart here, this table here, is from those guidelines. And they're arranged in ways that may not necessarily be obvious. If we look at a space and by what functions there, would sort of fit our typical patient rooms as they're required to be served. And they get a higher degree of air filtration than you would find in an office area, an area where we don't have inpatients, for example. So for each space, it'll detail what kind of filters you need to have in which filter bank. So there are actually two filter banks for inpatient care, and they rate the filters by something called a MERV rating. It's MERV, and it's a strange acronym, so I'm not going to bother to give you it because it's really just trivia. But suffice to say, it has a number. It has a number rating. So the first filter is required to be a MERV 7, and the second is required to be a MERV 14. This rating refers to the filter efficiency of that filter, meaning how much particulate matter it's going to filter out as the air passes through it. So a MERV 7 filter is a 30% filter, which will filter out 30% of the dust, and a MERV 14 is a 95% filter. So you'll get a very, very high degree of filtration. You get the same level of filtration for Class B and C surgery areas, inpatient diagnostics, and so forth. It's a high level of filtration. In protective environments, you'll have a MERV 7 pre-filter and a HEPA filter, a MERV 17 on the terminal end, which is an even greater degree of air filtration. Less so for labs with a MERV 13, which is an 85% filter, or a single MERV 7 for admin type areas. So how does this work? If we go with the first example being a regular office area, we have our air handling unit. The air comes in through the louvers. It passes through the MERV 7 filter, which is a 30% filter. And so what this means for us is that 30% of all the dust is captured here in the filter, but 70% of that gets through, and we're delivering 70% of that dust downstream. Okay? So none of these filters are perfect. They do not take out all of the dust. If we move up to a patient inpatient room, the air comes through, it passes through the MERV 7 pre-filter, it then passes through a MERV 14 filter, and then is delivered to the patient. So through the first pass, 70% of the dust gets through. Through the second pass, because a MERV is a 95% filter, 5% of that gets through, leading to a total, if you want to do the math, 3.5% of the dust gets through. But that's a very, very clean environment. It gets even cleaner if we go to a protected environment where the air passes through a MERV 7 filter and then through a HEPA filter, and less than 0.03% of the dust that's in that air gets through. So we have these degrees of filtration. Now, air exchange is the last bit that these systems supply to us for our patients. The HVAC system replaces, and I put that in quotes, replaces air in the rooms at specified rates as specified in the FGI guidelines. We refer to it in industrial hygiene circles as dilution ventilation. And quite simply, it means you're taking that air in the room and you're adding more air to dilute whatever odorants are in there, or body odor, or the buildup of carbon dioxide from people breathing in the air and exhaling in the room. So these are expressed in air changes per hour, or ACH. And there are total and outdoor air exchanges specified in the FGI guidelines in Table 7-1, but this is a summary of them in terms of the total amount of air exchanges you need. And you would expect that you would have higher amounts of air exchange in a critical area like a surgery area for B and C surgeries, slightly less so at 15 for trauma, A surgeries, laser endoscopy suites, 12 for a protected environment, 12 for an airborne infection isolation room, 10 for the anteroom for the airborne infection isolation room, and then down to 6 for labor, delivery, recovery, and office spaces. But these are all specified in the guidelines. So where's the risk? Well, the risk comes from a number of places. It can come from HVAC system modifications, from operations and maintenance tasks like filter replacement. Energy conservation systems can actually contribute to infection risks, as well as construction work on HVAC systems and other types of construction work. So the modifications that happen quite typically are what are called tap-ins, the making of connections or the disconnecting of ducts, because that changes airflow and the amount of air through a system. The installation of additional ducts or providing additional services, duct rerouting, temporary HVAC sources are all referred to that as tap-in. And it's the airflow changes that can change things for our patients and what we're delivering. So to the simple modification, this is sort of the standard room that we're working in. The air comes through the fan. It's delivered at 1,000 cubic feet of air per minute. It's being exhausted and recycled at 750, which leaves us a 250 CFM surplus, or amount of air that's going to go through leakage points. So our plan here is to build a new room over here and tap into this duct. And so let's see what happens. We build the room, we tap into the duct. Well, that 1,000 that was originally being delivered here is now split between two. So 500 CFM is going in here, 500 is going in here, 750 is being recycled out, which gives us a net deficit of 250 CFM, and this room ceases to be positively pressurized and now becomes negatively pressurized. And this will happen, I see this quite frequently when people do sort of their own, quote, home improvements in healthcare. They'll just tap into a duct, or we'll change this duct, we'll move something to another place, and they're not looking at the big picture, and they can change things downstream. So really, fundamentally, what I'd like you to leave with is any change we make to the duct system affects the ducts someplace else and affects airflow. And these modifications happen in all kinds of environments. Some people don't like air coming out of diffuser and blowing down their back, so they will take off this diffuser cover and stuff in a blanket. And so what that blanket can do is then that air that was flowing through there can't get through, so it backs up. It pressurizes the duct. That duct becomes pressurized, and through leakage points in the duct will pressurize the above ceiling space, which is where dust accumulates in the environment, and will push that dust down into the environment. And this was a cause that we identified in an aspergillosis outbreak in a neonatal intensive care unit. This was either done by parents or by staff or by both. This was not a natural thing to occur, and it ended up causing infections in a couple of patients. Other things that can happen, the unintended consequences. In our advanced computer age, where we're in buildings, in older buildings that weren't designed for computers, computers are now a new source of heat. And so you have a computer and you have a monitor. But what's becoming the new normal is now having two monitors, which is more heat. And in high-end places, it's having 3 monitors or having a computer on wheels. So we generate a great deal more heat, but we don't upgrade the HVAC system. So a building will turn to the engineering folks and say, gosh, what can you do to make it cooler? It's so hot in here. And so what they will do is decrease the temperature in the cooling coils in the HVAC unit, and they'll oftentimes increase the fan speed of the fan. Well, by doing that, the temperature falls, can fall below the dew point, and you will get condensation in the cooling coils. And that water will create water droplets that then blow in the airstream and will blow out the back and into the back of the HVAC unit, which is covered with sound insulation. But as we know from the filters, they don't entrap all the dust. Some dust gets through. Some of that dust contains mold spores. Those mold spores get wet and things grow. This is not the natural color of this. This was supposed to be that kind of white color that you see. So every darkened shade is a colony of mold. And here on the coils themselves, where dirt gets stuck, if they stay wet, you can grow mold on these as well. And this is a risk for our immune-compromised patients down the road. The other piece is when you increase the amount of water flow, sometimes the drip pans that catch that condensate don't drain properly. And if they don't drain properly or they overflow, you can get growth in the pan, and you can grow mold, and you can grow algae, you can grow all kinds of things, and that's in your airstream, and you're delivering it straight to the patients. So this is something to keep an eye on. Other routine tasks that we think are going to be good for us can not always turn out that way. Filters are routinely replaced in the HVAC systems, and it's a great opportunity to inspect the gasket integrity to make sure that these filters are fit, that they conform to the size, that they're the right kind, and you get a nice seal. But if we don't look for that, we'll never know. So there are techniques of measuring this using laser particle counters to show, and something that I recommend is done every time you do that, just to confirm that they're working. But there are other ways of using high-intensity visual background lighting and going on the other side and looking to see if light leaks through. And if you see that, you know you're getting filter bypass. Unfortunately, most people that change filters, whether they're a contract person or they're your own people, they're trained to just, quote, change the filter. Just go up there and change the filter. So they're not being asked to look to see if the gasket is missing. They're not asked to look are we missing a gasket and are we seeing dust accumulating on the frame like we do here. That's all an indication of bypass, which means the filters were not working like they should be, and we're not giving our patients the type of filters they're supposed to need. So this is something that really needs to be done, in my opinion, on a regular basis. Here we have the same filter frames that had the leakage and bypass, and here we are replacing them with new filter gaskets. They all deteriorate over time. They hadn't been looked at in 30 to 35 years, and they had all just worn away, and nobody knew to look. So it's an important thing to keep an eye on. Then there's energy conservation, which is pretty much always an issue for me. There's a new piece of equipment I'm going to introduce you to called a VAV box. It stands for Variable Air Volume Box. And its purpose is to restrict airflow. If we're in winter, for example, and you have that cold air coming in from the outside, it's very expensive to heat. It will dampen it down in a localized area, and you'll provide additional heating from that source. So it can increase airflow to other ducts if one of them goes off, and that can be a potential issue. The other type VAV box draws air that's either less or unfiltered from the above ceiling, and they look like this. We have the air coming in from the HVAC unit from the outside. It's ducted, and it comes down here to the box on the left that we'll call, for all intents and purposes, a squeeze box. The air is supposed to come down this way. This is open at 50%. If it's closed, it completely blocks it off, and no air can get through. If it's open, it's completely vertical. And all it does is restrict airflow, but when you do that, it increases the airflow to other ducts, which could be an issue and could change pressurization in other spaces. The other type VAV box has a fan in it. It's a powered VAV box. It has a fan. It has louvers that will stop the airflow coming from that cold air from the HVAC unit, from the air handling unit, but it will draw air from above the ceiling, which has already been filtered in theory and already been heated. So it'll draw air from above the ceiling, but above the ceiling is where we accumulate dust. So if we don't have a filter here, that dust is going to come through and you're just going to blow it down on our patients. Or it has a filter, but those filters are really borderline useless. The best you'll find for them is about a 30% filter, a MERV 7, but typically they're just an open fabric filter that don't catch very much dust at all. And that can be an issue if we have these where our patients are. The last piece of energy conservation is a balancing between buildings. Hospitals will often expand and build wings, or you'll have a clinic or a small critical access hospital actually connected to a shopping mall or some other big building. So I use this for explanation purposes over. This is not a place that I've been to or seen, but it illustrates what I found at another place. So here on the left, we have our idealized hospital, which runs 24/7, and it's just a big bruiser of a building, and it's getting lots and lots and lots and lots of air. Over on the left is our little ambulatory surgery clinic that we've connected to the hospital. And it's the little engine that thinks it can, and it does fine during the daytime where it's pumping all kinds of air into the ORs and into the building, and you have a nice balance between these two buildings. But come nighttime, when we don't have a need for the surgery center and things close down at 5 o'clock and everybody goes home, to save energy, they will shut down the air handling units. Now, I say shut down, not exclusively off completely, but they will reduce the airflow upwards of 50 to maybe even 60 to 70%. And by doing that, this little engine that could is no longer balanced off here with the hospital. The hospital is now pumping air into here. And what has happened in a building that I inspected, and I learned this the hard way, was that at nighttime setbacks, we were getting air, untreated air, from the adjacent building, and it was blowing into our surgery suite. And what I stepped into was a big, big argument between infection prevention and environmental services who was saying that we are cleaning the space, and infection prevention is saying, then why are we seeing dust in it every morning? So I happened to be there in the late evening, and I'm measuring it, and airflows were perfect between the two buildings, and I'm making some notes, and I look down at my feet, and I watch a dust bunny roll across the floor right in front of me, and I thought, well, that's weird. At the same time, I had noticed the sound changed, and the amount of airflow had stopped, so I went and corrected and took my measurements and discovered that because this had gone into economy mode, that we were getting unfiltered air and dust from the adjoining buildings. So it's important to recognize which is working that the systems are working and they're properly balanced for both night and daytime. So operations and maintenance systems inspections that are recommended in the guidelines. Now, this references Section 6. Yes, it's in Section 6, but it is in Appendix A at the very back of the guidelines in the 2010 and 2014 guidelines. And these are non-mandatory recommendations, but they are very sound recommendations. They recommend that the ORs be checked for positive pressure on a semi-annual basis. There's no downside to doing that. That the protected environments, that the positive pressure check be done daily when there's a patient present, an immune-compromised patient present. Nothing about that does not make sense. It's a great recommendation. For AII rooms, negative pressure checks on a daily basis when infection patients are present. And that filters and filter frames, and this is overlooked by pretty much every engineering department, I would venture to guess almost in the country, that final filters and filter frames to be inspected visually for the presence of pressure drop and bypass on a monthly basis. That's a very, very good idea, and you can roll that into the quarterly air filter changes. Other things from that same appendix, that if you have what's called a fan coil unit or heat pumps that serve patient rooms, which you'll find in our older hospitals, they need to be inspected monthly for pressure drop and airflow, and that the drains under the cooling pans be checked for moisture and make sure that they're cleaned monthly. If you have fin tube radiation units, like we do in some of our older hospitals, you need to have them cleaned quarterly because that's where dust will accumulate, and if they provide cooling, you can get them wet and you can grow mold in patients' rooms. And then if you have fan power terminal units, the same thing. You need to inspect the filters monthly. These are all very, very sound recommendations. And I have my own to add that I think that when you do change out all filter replacements, you need to do some kind of filter efficiency testing to either measure and prove that they're working properly, or secondly, do that light inspection to make sure there's no visual bypass. And any time that you change a motor or a belt or the wheel, what's called a shiv, on a fan inside an air handling unit, you need to check that the directional airflow in the rooms is still going the right way. Anytime you do a change to a duct system or an HVAC system, you need to check to make the airflow is still going the same way. And you do need to check for nighttime economy mode and energy saving mode to make sure you've got the directional airflow that you need. So to summarize, HVAC system basically protects patients and staff from what's outside. We need to understand how the system works, and hopefully those really keen drawings are going to work to do that for you. It's not rocket science. It's actually quite simple, and the concepts are the same. And feel free to bring those out if you feel you're getting the runaround from an engineer or a mechanical contractor. And again, inspection is the only way to know that you know that the system is working as designed. Please don't leave it to trust. So that's HVAC systems. Now I'm going to go through plumbing systems. This is going to include potable, non-potable water is generally provided from a source, out there in the environment by a city, municipality, or a water district. At the source, at the lake or at the underground well or at the river, we treat the water. It's treated with chlorine, chlorine dioxide, monochloramine, or ozone. But yet, despite what we do for these treatments, Legionella bacteria enters the water system from the source and can grow and amplify in plumbing systems. And Legionella is a source of Legionellosis, or Legionnaire's disease, as has made the news in some local communities here in Washington State and made big news in New York City last summer. There are basically 50 Legionella species, 50 types of Legionella bacteria, 19 of which are human pathogens that can cause Legionellosis. Legionella pneumophila causes roughly 90% of the infections, and of that, serotypes 1, 4, and 6 cause most of the infections. Legionella, in terms of their ecology, they're dependent on fresh water and soil, and they're dependent on biofilm, which is a small little micro ecology that's built up of algae and amoebas and paramecium and all kinds of microscopic life. And Legionella is an obligate parasite, meaning that in order for it to reproduce, it has to be eaten by something. It has to be consumed, and it parasitizes it. So they're typically eaten by amoeba, which are eaten by paramecium. And as the Legionella reproduce inside the paramecium or the amoeba, it releases toxins that kill the host lyses, and then free-floating Legionella are in the water, hoping to be eaten by other amoeba and paramecium as life goes on. They can survive at temperatures from 41 to 145 degrees Fahrenheit, but they thrive in a special zone between 77 and 104 degrees. And they are capable, as biofilm is capable, of colonizing water systems, including cooling towers, pipings, ice machines, water fountains, and so forth. So pretty much anywhere you have water, you can have biofilm and you can have Legionella. Now, there are community sources of Legionella out there, and it's all water systems, domestic water systems, spas, whirlpools, sprinklers, cooling towers are often emphasized, and in my view, overemphasized in terms of sources, but vegetable misters, humidifiers, and all the rest. There are specific hospital sources, which of course is the potable water systems that we consume, spas and jet tubs, ice machines, and I will talk about ice machines in detail, humidifiers, dialysis water, cooling towers, emergency showers, and then specifically community sources and hospital sources, there are things known as dead legs. And dead legs are dead-end pipes that are capped off but not connected to the, but are still connected to the water system. So it's sort of this dead-end little pool, if you think of, a little slough out there that nothing much happens and things grow in it. So dead legs, where are they? In hospitals that are remodeled or a patient room is turned into an office, they'll turn that shower into a closet. And this is what I discovered at one hospital on a walkthrough. I said, oh, look, nice, you have a closet in here. They said, no, it's a shower behind it. Well, this is a dead leg. This hadn't been used for 5 or 6 years, and that is a bit of pipe that has water in it that things will grow in simply because you don't get circulating chlorine from the city water to disinfectant. The chlorine gets all used up, and then things can grow, and that can be a source of Legionella. Other places are in the units themselves if they're under construction, where you will have doing a big tenant improvement, and you'll have water system pipings that run through here, and all about they're connected, but they don't get any water service because all the plumbing's been turned off. Well, that is a huge dead leg that'll become an issue once the water gets turned back on. So the risk factors for Legionella are advanced age, being a male, smoking and alcohol abuse are issues, chronic pulmonary diseases as well. But it's also a disease of children. You'll find immune-suppressed children will get this through transplantation, or if they have HIV or late-stage AIDS, or some underlying pulmonary disease. So we shouldn't forget about them. Now, the modes of transmission in healthcare, which I think is the most prominent mode of transmission, and I think it's under-recognized, is aspiration or microaspiration from drinking. And imagine that you're having your morning coffee, your morning tea, or your morning hot drink. When you take a sip of it, you go as you come across the top. Well, every time you do that, you're creating some aerosol. And any time a liquid is poured, it creates an aerosol. And if that aerosol contains Legionella in it, bacteria, that will go down into your lungs. And that's where the disease will get a foothold for you. So it is under-recognized, but it's an important thing in which I'll talk ad nauseum about ice machines. But intubation is a risk factor. Surgery requiring anesthetic is a risk factor. Nasogastric intubation. But then there's standard inhalation, which most people think about, which is nebulizers, whirlpool spas, water features that have drips and droplets, as well as cooling towers. And then there can be exposure through contacts through wounds. So moving to ice machines. Ice machine, or should I say enemy, thy name is ice machine. There's a bunch of components here. This is the reservoir where the water is stored for use in the ice machine. Down here is the compressor, which refrigerates this and keeps everything cold up above. But these machines, these compressors, generate a lot of heat. The heat rises, and it heats the water reservoir and can cause things to grow and amplify because they get warmer. So here's a close-up of it. Now, this ice machine, this water reservoir serves two things. One is the water that's dispensed out of the ice machine for, by glass to patients. The other is a water tube that comes down and hits the actual ice machine and auger, which creates a tube of ice, which flows down here into the big storage bin. Okay. So what happens? Well, we had a case where 2 people died from legionellosis in a healthcare setting, and their only contact with water in the hospital was through ice and drinking water. That was the only contact they had. So I went straight to the ice machine, and I took a swab inside here, and this is the swab. And the swab in a clean ice machine should be nice and clean. There shouldn't be anything on it, but you've got this little brown thing here. Well, that's residue, and that's biofilm. So we did a bunch of sampling of the machine, and here's what we found, that the swab that we took from the reservoir had 900 CFUs of Legionella in that swab. The ice had 750 CFUs. This is ice, and this is culturable living Legionella bacteria. The drinking water supply tube had almost 3,200 CFUs in the swab. The dispensed water had 4.4 CFUs. But interestingly enough, and this I think illustrates the point, is that the source water coming through this tube, bending around, was sampled, as well as the water coming out of the filter that the source water was going into. We detected no Legionella. So what this means is the water source was really fine, was looking good, but a few bacteria at one time got through, and it was able to amplify in the ice machine. You'll never get ice again from anywhere, I'll tell you after this. Then there's the big dispensing ice machines, the high volume ice machines. Many of them have a big bath or a big sort of water reservoir that runs in a tray that runs along the whole length of the ice machine itself. And it gets wet and it can grow things, but interestingly enough, because it's not insulated, the temperature here is often below the dew point, and you will get things that are wet here. There'll be dust that'll accumulate, and it'll grow mold and other bacteria inside the ice machine, which is, kind of gross. So let me know if you're ever going to drink iced tea again. So what we do, if we have a point source like we did in the ice machine, the first thing to do in terms of response is to take it out of service. You need to clean it, descale it, disinfect it, and then test and sample it. And you need to validate that it worked. Just don't trust somebody that, we cleaned it and it's fine. We really need to prove that it's fine, and you need to test after that. And what I recommend is that you test monthly for the first quarter, and if that comes out all negative, then you go to quarterly and then annually to make sure that your PMs are working. But you need to review how frequently you're doing. You need to review the procedures and make sure that it's being done. Now, cooling towers. I'm always obligated to talk about this because this is what draws everybody's attention and makes the news media. So what is a cooling tower? It's a device that's used to cool liquids that are sent to it. So we have hot fluids that come in through this pipe here, and like a radiator, they bounce down through here, and ideally they're cooled, and they go back to their source, they get heated up again, and they come back in this loop, okay? Now, we don't worry about this because it's a closed-loop system. There's no way we're exposed to this water. Now, the way we cool it is that above it, we spray down misted water on top of it, and that water falls down. It's cooler. It falls down, cools the piping, accumulates down in this bath down here. It then, for efficiency's sake, is piped and pumped right back up and recirculated. Okay. So over time, what will happen is this water will get warmer and warmer and warmer. And this will get warmer and warmer and warmer, and it will promote growth simply because we're using water from the outside, but we tend to not treat it very well. So things will grow. Now, in and of itself, if it just stayed here, that would be great, but that's not how a cooling tower works. It has a fan on top, which is supposed to blow air out away from it, but it draws air here across the bottom. from this side and from this side. And so as that air is drawn up by the fan, it will also pick up aerosolized mists from the cooling tower and blow them out, and they'll settle for a mile or 2 miles away. And these have been implicated in a couple of outbreaks, but again, I think it tends to be focused upon, whereas really the main sources of it are microaspiration from domestic water consumption and ice consumption. Now, these units can be large. We need a ladder to get up to see them, but it's the same thing. Here's the bath down here. This is the grill for the intake for the air to move in, and then here's the exhaust discharge up for the fan. But they can be small. They can be hidden. You may not even know that your facility has one that's used to spot cool some equipment like a CT scanner or something like that. So again, quick review. You can get amplification of the bacteria in the water cooling loop. It'll grow in the pool. It could grow in the cooling water piping, and it can grow on interior surfaces. The aerosolization of the mist, if it contains Legionella, it does create a risk, but we have to address the biofilm. Sometimes we think if you just kill the Legionella, but you have to kill the environment, destroy the environment that it lives in. If we don't do that, the Legionella will persist. So removing the biofilm is a primary goal. And if you're going to be doing this work, the people that are doing it need to be wearing an N95 filtering face piece respirator at a minimum and use gloves to make sure that they're not exposed to it. Now, if you have a system-wide contamination or a system-wide outbreak that we're concerned with, the responses are much, much greater, and they're much more much more of a big deal. I'll keep it simple. So if you have a unit or a loop or a facility, there are a number of treatments that people do, and the easiest one to do is what's called thermal shock, where you increase the heat of the hot water system to 160 degrees as measured at the most distal outlet. So you're probably heating the water to 180, 185 at the source. And you do that for about 3 to 5 days, and you flush every single tap, shower head, distal outlet for 30 minutes in order to make sure that you've killed that biofilm, you've killed the Legionella throughout. Then you need to cool it down and flush the entire system. And you might have to repeat this every 3 to 5 weeks because it's not a permanent solution generally. And most of these solutions may not be permanent. You're fighting a biological system, and life will somehow find a way. But this is what's used quite routinely, especially on an emergency basis, because it's perceived the easiest and quickest thing we can do. There's also hyperchlorination, where you add chlorine to it, where you want to get a total circulating amount of 50 parts per million free chlorine throughout the entire system as measured at the distal outlets. You want to do this for a 12 to 24-hour period, and then you flush it through. But there's also copper-silver ion treatments. They can be expensive, but they can be very effective. The downside is that it might turn you into a water treatment facility, which has its own different licensing requirements. Chlorine dioxide is used, monochloramine is used, and sometimes point-of-use filters are used. I think Paul Medical makes them. I'm not sure if they're the only one or not, but that you could put in to protect your at-risk patients immediately to make sure that they're getting properly filtered water. And then you need to validate that these systems are working, these changes are working, and then maintain them on a standard maintenance plan. But the key piece for me is those are your options. You don't want to be thinking about those when you have an issue because it's just too crazy. It's just too much stress. The idea is to find out whether these things are going to work before you have an outbreak. So everybody likes to run to thermal shock, but can your system deliver that kind of high temperature water to the system? And then can your system survive it? There are a lot of plastic pieces and polyvinyl pieces that are now in plumbing systems that might be damaged by this, and suddenly you might have big leaks and leaks of very, very hot water. So that's something to check out beforehand. And because there is some subtlety and nuance to hyperchlorinization and silver copper ion and monochloramine, you need to work with the vendors and pre-qualify a vendor that you're going to have come in and do this for you. And one of the things the vendor does is make sure that your water is capable of or is compatible with hyperchlorination or copper, silver, or monochloramine. If you don't, you could spend a lot of money on hyperchlorination and nothing works if you're not able to maintain the right pH of water, for example. So the way to pre-qualify vendors, at least in my view, is really to call them in one at a time, and they tend to focus on one method over another and have them tell you about their method and how good it is and tell you why all the other methods stink and don't work. And then you have the next vendor come in and do the same thing, and then you'll have a good, clean picture of what's going to work for you, what's going to work best, and then ask them about how they'll be able to mobilize and support you in case you have an issue. Then following that, you need to have a disinfection validation plan. You need to be sampling and proving that the system is actually working. So the management approaches to this can vary, but I think very soundly thing to do is to check, is to inventory your distal outlets. Know what kind you have, because you may find that you have 5 or 6 different types of ice machines. And if you have an ice machine that's generating Legionella, maybe the other ones aren't, and so you'd want to separate those out. Same thing for faucets and handless faucets and motion detector faucets and all the rest that is out there. You also want to identify your dead legs and either remove them or cut them off, cap them off, and isolate them. You don't want them connected to your system because they are important sources of biofilm and Legionella. You also want to keep your ice machines on a very strict PM schedule. And I think everybody should be doing that today and make sure that it's being done and being done with the manufacturer's recommendations, because in my issues, that's important for us. Okay. Oh, PM stands for preventive maintenance. Thank you. That's Jamie here talking to me. So just make sure you're looking at those. You need to monitor your cooling towers, and then again, pre-plan and test your response capabilities. So I'm going to close with some references that are very, very good. The ASHRAE standard 188 is really the state-of-the-art standard. It was just passed this past July, and that is really what governs what we're doing. And you may have found that your institution has said that they've adopted it. Most places haven't, but it's important if you're going to. And it gives real nice step-by-step ways of managing it. But there are other sources out there, and I leave them to you. So I see I've hit my 11:50 mark, and I guess now I'll turn it over to questions. Thank you for your attention.
If you have a question for Larry, now is a great time to ask. Sarah, our producer, will open your line if you'll click the raise hand feature. You're also welcome to chat in a question to us. However, I do want to caution you that you need to select either all participants or select to Jamie Moran so that we can see the question here in our office, and we'll read that question to you.
It looks like Dorothy has a question. I'll go ahead and unmute her line.
I think you're on, Dorothy.
Oh, okay. Hi. So I'm an epidemiologist in Spokane. We did have a Legionella outbreak at one of our hospitals a few years back. And so our hospital ended up doing that hyperchlorination and heat treatment of the water at the same time, and it started, relatively in short order, and that seemed to be pretty effective. Have you seen that elsewhere, or?
I haven't. I've attended a couple of presentations that was put on by the hospital that will be unnamed, and they spoke about it, and the takeaway that I got from them is that they had wished that they had vetted this beforehand. To take away a lot of the stress and anxiety of because they really didn't know that they could deliver that kind of heat. but they selected both. I mean, they went for both method, and they turned out to be compatible, and it worked. And so, my hat's off to them. My involvement with outbreaks is I have not found them on a how do I put it, on a large scale, that ran through a whole hospital, but really were point sources, and those point sources, by and large, were all ice machines.
Okay, and so that's my other question. That sort of is in back of your feeling that more of the cases occur related to ice and aspiration rather than the ventilation system or shower heads or things like that?
That's what I've seen. That's my experience. Now, we did look at a whole host of other things, but for me, when these two patients, their only water contact was ice and water. I mean, it couldn't be any more clear. And this had happened when microaspiration was being suggested in, I think it was an AGIC or some other publication. They said, we think this is how it's happening. And so I believe it's under appreciated, and a lot of effort is put towards cooling towers, which I don't want to poo-poo it. Legionella does grow in them. But in a healthcare setting where people are in highly filtered environments, I really don't see, unless they spend a lot of time outside of their unit, that's where they're going to get it from. And this is focusing on healthcare, not so much community. But another piece that happens in these investigations is I will often ask, has anybody looked at the patient's home? There's other organizations I work for that have let's say cancer patients that come in on an outpatient basis, and they go home and they're monitoring their condition afterwards, and they've developed Legionella. It turned out not to be, there was no Legionella found in the clinic that they visited, but nobody looked at their homes. And on the one hand, from an emotional standpoint, I can understand you don't want to go to somebody's home, find Legionella, and tell them, that contributed to the death of their loved one. But I think in larger epidemiological studies, from looking for a community source, that's something that really should be done. And it may open an ugly public health can of worms, but I think it's important.
Okay, thank you.
Does that answer your question? Okay, Dorothy.
Yeah, it's interesting how you
stated
in the outbreak, just general case investigation, and I don't think that we do focus more on like inhalational sources like humidifiers or hot tubs or things like that, but I don't recall, chatting with anybody about ice or their water sources necessarily.
Well, it's led me to become the ice machine preacher.
Thanks, Larry.
Thank you. It looks like we have a call from Margie at Peace Health.
Hi, can you hear me?
Yes, I can, Margie. Hi.
Okay. So
well,
I just
feel like
had a
radio
question.
Talk show host.
I just had a question around the ice machines as well. I'm one of the infection preventionists here at Peace Health Riverbend Hospital in Springfield, Oregon. And you mentioned doing swabbing. Is that something you would do on every? I'm thinking the sheer number of ice machines in any facility. Is that something you would do on a yearly basis, or what's your recommendation for those?
Well, I think it's taking that first step is trying to establish where we are today. And if you're going to establish where we are today, you need to have everything else in place in case you get unfavorable findings. So from my perspective, to keep things moving is to get a few spare ice machines ready to go in case we find something unfavorable. From there, I tend to be methodical in my sampling, and so I think you sample the water that comes out if it has dispensed water. I think you sample the ice. I think you also swab the water reservoir. And in some case, and what we did in our case here is that we would actually dismantle the tubing because I think plastic tubing also lends itself to biofilm formation. And I would swap out the tubing at that time and cut that up and send it to the lab, and they can vortex it and plate it out and see if they grow it. So those are the main things that I would look for in ice machines.
Okay, thank you.
You're welcome. Okay, somebody has chatted in, how does humidity affect the OR? We're required to basically keep OR relative humidities between 30 and 60%, and I believe it's recently been lowered to 20, although I guess I can't quote myself on that, but so we'll stick with the old 30 to 60%. So there's two issues with humidity. If humidity gets too low, gets in the 20% range and lower, you can get electrostatic shocks and develop charges on things, and that can affect instrumentation. That can cause someone to get a shock from their gown, possibly, or some other piece that has developed a charge, cause them to jump, and that can cause issues. The other piece is it can be too moist, and it's commonly believed, I guess is what I should put, is that if you have a relative humidity above 60%, that you can cause mold growth in an OR environment. And I disagree with that because fundamentally you need liquid water in order for mold to grow. But the point is if you have a relative humidity above 60, if the temperature of some piece of equipment or wall board or something is below the dew point, you can get mold growth because you'll get condensation on those. So that's largely the issue about high humidity. So that covers the low end and the high end. The second question that's come in here is, does the air into an OR need to be HEPA filtered? That's the first question. I'll answer that. The answer is yes. It most definitely does. In the FGI guidelines, it requires a MERV 7 filter to be first and a HEPA filter to be there afterwards. So absolutely yes. Is it the current standard to have UV lights in the HVAC system in an OR? No, it is not. Facilities will put them in, and the rationale is largely, I guess it's sort of multiple rationales. Whoops, I just lost my screen. But it's not the standard to put them in there. The FGI guidelines don't necessarily recommend that. You might, if you have a special population, if you're doing bronchs on TB patients, it might put that in. Some people put them actually in the ducting, and they'll do that to prevent, in an attempt to prevent mold growth inside the ducts, inside duct locations. But no, it's not the current standard to have that. Are there any more questions? Okay, well, thank you all very much, and I'll see you next time.